Since antiquity, we've been obsessed with the idea of creating artificial life. Long before microchips, inventors were drafting blueprints for steam-powered birds and spring-loaded mechanical knights, dreaming of machines that could move with human autonomy. But when the modern robotics revolution arrived in the 1960s, it looked entirely different. It looked like the Unimate. This was the world's first production industrial robot, a massive hydraulically powered arm built for heavy manufacturing. For all its power, the Unimate had a specific limitation. It was completely blind. It operated on hard-coded trajectories, mindlessly repeating the exact same sequence of spatial coordinates with zero awareness of its surroundings. Because these massive machines couldn't see or adapt, we couldn't place them into our chaotic world. Instead, we built perfectly predictable, rigidly structured environments entirely around them. This diagram illustrates the 6 degrees of freedom standard, pioneered by early systems like the Stanford arm. A robot needs 3 axes of translation: up, down, left, right, forward, and back, and 3 axes of rotation: roll, pitch, and yaw. Giving a heavy machine total spatial reach created a dangerous hazard. If a human unexpectedly stepped into the robot's pre-programmed path, the machine wouldn't pause or reroute. It would simply swing through its coordinates, striking whatever was in the way. The only way to harness this power safely was absolute physical isolation. Industrial arms had to be bolted to the factory floor and locked behind heavy steel safety cages, entirely separating human workers from the machinery. The defining characteristic of this industrial era was that the robot could not adapt to our world. We had to adapt our world to the robot. But what happens when you unbolt the machine from the floor? When a robot leaves the rigid geometry of the factory, it immediately faces an environment filled with moving people, scattered objects, and constant change. Engineers call this the unstructured environment. To survive here, a robot cannot rely on a pre-programmed path. It has to navigate on the fly and dodge obstacles in real time. The first machine to seriously tackle this problem was Shaky, developed at the Stanford Research Institute in the late 1960s. Shaky utilized early artificial intelligence to reason about its own actions before its motors even engaged. This shifted the burden of robotics from purely mechanical engineering toward cognitive software. To move freely through physical space, the machine needed a method for making independent decisions. That system operates on a continuous 3-step loop: sense, plan, and act. First, it senses its state. It tracks wheel rotations, firing laser pulses, and capturing images to measure the room's physical boundaries. Next, it plans. Using the SLAM algorithm, it analyzes those pulses to construct a grid map while pinpointing its own location inside it. Finally, it acts. The software plots a safe trajectory to its goal and translates that path into precise motor commands, actively adjusting its wheel speeds to steer around anything that wanders into its path. Mastering this pipeline allowed machines to permanently leave the factory floor and step into environments that are impossible to pre-program. By looping through sensing, planning, and acting dozens of times per second, the robot transitioned from a blind, repetitive tool into a perceiving, deciding agent. Today, we are witnessing the collision of these 2 historical eras. Immense physical capability of the industrial arm is merging with sensory intelligence developed for mobile navigation. This convergence created collaborative robots, or cobots. These machines are designed from the ground up to operate right alongside humans, sharing the exact same workspace without a single physical cage. They achieve this through sensitive force-limiting joints. If the arm bumps into a worker, internal sensors detect the resistance instantly, halting the motor before the impact exceeds strict biomechanical safety limits. Instead of being isolated to rigid assembly lines, workers can physically guide the robotic arm to teach it new motions, allowing humans and machines to tackle highly variable tasks on the same floor. The heavy steel cages of the past have evaporated, replaced by invisible safety barriers woven out of software and real-time sensory feedback. The brains of these machines are scaling accordingly. Thanks to standardized software frameworks like ROS2, developers can completely separate a robot's hardware from its cognitive logic. Because of this abstraction, the exact same mathematical navigation stack can drive a wheeled warehouse vehicle, balance a legged quadruped, or guide a service robot through a hospital ward. The trajectory of robotics is shifting from machines that require a customized world toward machines that can understand our world. By prioritizing the ability to perceive, plan, and act, the field is transitioning specialized factory tools into intelligent agents capable of navigating human environments.